In this video, I'll go over how to formulate Lagrange polynomials. After studying this video, you should be able to formulate a Lagrange polynomial and use a Lagrange polynomial for interpolation. So what's a Lagrange polynomial? It's basically a stylized way of writing a polynomial. And so here's a couple examples. A first-order polynomial, we know a simple polynomial would be f of x is equal to some p1 of x plus p2, analogous to that y equals mx plus b, or the equation of a line. And the Lagrange polynomial would be written as L1 times f of x1 plus L2 times f of x2, where f of x1 and f of x2 are known data values, and L1 and L2 are called weighting coefficients, and they are functions of x. So this can be a little bit confusing. This f of x1 and f of x2, those are basically y data points. So a second order Lagrange polynomial, which is indicated again by f2 of x, we have the simple polynomial, which is basically a quadratic equation, p1 times x squared plus p2 times x plus p3. Written in Lagrangian form, it would be L1 times f of x1 plus L2 times f of x2 plus L3 times f of x3. Again, these f of x's on the right hand side are y data points, and the L's are all going to be weighting coefficients. And again, they are functions of x. So in general, we can write an n-1th order Lagrange polynomial as a summation of n terms, where each term is the weighting coefficient, which is a function of x, times that y data points, which we're calling f of x. So let's look at how this works with a first order polynomial. So here's our first order Lagrange polynomial, and again, this is just a stylized way of writing the equation of the line here that's connecting these 2 points, this point as x1 f of x1, and the second point here as x2 f of x2. So we know we can write the equation of that line using slope-intercept form or other forms, but the way that a Lagrange polynomial is going to work is we're going to write it as the sum of 2 lines. So each of these is going to be a line, and the line L1 f of x1 is going to be a line that's equal to 0 when x equals x2 and equal to f of x1 when x equals x1. So we can imagine that first line, line 1, would be a line that looks like this. And then the second line, line 2, that we get with the second weighting coefficient, would be a line that looks like this. It's equal to 0 at x1, and then f of x2 at x2. So anywhere along the way, we can add line 1 plus line 2, and we get to our initial value. So this value, for example, right here, would be equal to our value from line 1 plus, at that same x location, our value from line 2. So let's look at how we can define that. So if we want to get that first line, line 1, we can write that as x minus x2. So now we know that it will go to 0 when x equals x2, divided by x1 minus x2, all times f of x1. So let's look at how that works. If we plug in a x2 there, then the whole thing goes to 0, and that's what we want. We want that to be equal to 0 at x2. If we plug in an x1, then this first weighting coefficient, that weighting coefficient is going to go to 1, and then we have 1 times f of x1, and it's equal to f of x1 at x equals x1. We can do the same thing for the second term in our Lagrange polynomial, and that's just going to be x minus x1 in the numerator. That way we make sure that numerator goes to 0 when x equals x1, divided again by x1 minus x2 times f of x2. So those would be, this again would be our weighting coefficient L1, and this would be our weighting coefficient L2, and then we can write our final Lagrange polynomial, first order Lagrange polynomial, f1 of x is equal to x minus x2 over x1 minus x2 all times f of x1 plus x minus x1 over x1 minus x2 all times f of x2. Again, this is L1, and this term is L2. So we see L2 is a linear function of x, L1 is a linear function of x. And we'll just have a combination of two linear functions. And this might seem like an overly complicated way to calculate the equation of a line here. And, well, it is, but it's important to understand how to derive the first order Lagrange polynomial in order to understand how to derive higher order Lagrange polynomials. Recall from the previous video on interpolation that calculating and interpolating polynomial that's second order or third order or fourth order required the solution of a linear system of equations, and that system of equations gave us a Vandermonde matrix that was ill-conditioned and vulnerable to round-off error. So this is actually going to give us a way to solve for those polynomials without having to solve that linear system. So let's look at how we could derive a second order Lagrange polynomial. So again, that second order Lagrange polynomial, it's going to be a summation of three quadratics, L1 times f of x1, L2 times f of x2, and L3 times f of x3. Now, L1 times f of x1 is going to be a quadratic that's equal to f of x1 but goes to 0 at x2 and x3. So it might look something like this if we imagine that quadratic. It's equal at f of x1 is equal to f of x1, but when we get to x2 it is equal to 0, and at x3 it's equal to 0. So that L1 f of x1 might look something like that. L2 f of x2 is going to be equal to f of x2, so it's going to cross through f of x2 at x2 and equal to 0 at x1 and x3. So that might look something like this. That goes right through x3. And finally, L3 times f of x3 is going to be another parabola that's equal to 0 at x1 and x2, but it's equal to f of x3 at x3. So this is going to be a wide parabola coming down, maybe something like that. So let's use a similar approach to what we did before to calculate what would these weighting functions look like for those three parabolas. So for L1, we're going to have it's equal to 0 at x2 and x3. So in our numerator, we're going to have x minus x2 times x minus x3. So that's going to give us a quadratic second-order polynomial because we have two terms multiplied together, so we'll have an x squared term, and that's going to be equal to 0 where x equals x2 because we'll have x2 minus x2, gives us a 0 there, and it will be 0 where x equals x3 because we'll have x3 minus x3 equal to 0. So the numerator takes care of getting it to those two zeros, and then what we want to make sure of is where x equals x1, this weighting coefficient goes to 1. So just like before, we'll have x1 minus x2 and x1 minus x3. So if we look at that weighting coefficient, L1, again, it's going to be equal to 0 where x equals x2 or x equals x3, and 1 where x equals x1. And then in between it'll have whatever value it takes depending on the value of x. We can do the same thing for L2. So L2 is going to be equal to x minus x1, since we want that to go to 0 where x equals x1, and x minus x3 divided by x2 minus x1 and x2 minus x3. So that one, again, is going to be equal to 0 where x equals x1 and x equals x3, and it's going to be equal to 1 where x equals x2. Lastly, we can calculate L3 directly. L3 is going to be x minus x2, so it equals 0 at x equals x2, x minus x1, so it equals 0 at x equals x1, divided by x3 minus x2 and x3 minus x1. And again, that weighting coefficient then will be equal to 0 where x equals x1 and x equals x2, because either of those terms would be 0 in those cases, and 1 where x equals x3. And so together, these three weighting coefficients multiplied by the y data, fx1, fx2, and fx3, formulate that second order Lagrange polynomial. So we can generalize this for any order polynomial. Hopefully you can see a pattern here where the terms in the numerator are determined such that the weighting factor goes to 0 at points that don't correspond to the y point, the f of x1 point in this case, and the terms in the denominator are determined to cancel those out so the weighting factor goes to 1 when we're evaluating the polynomial at that data point. So let's look at that generalized form. Again, here's the generalized form, and then the weighting coefficients. Here's the generalized summation, where each Li is a weighting coefficient times f of xi, and again, that's the y data. Now, the n weighting coefficients Li are given by this term, and this is a product notation. So it's similar to the sum notation. This is what's defining those products, like x minus x1, x minus x2, and this would be for j not equal to I, so this might be for the x3 minus x1 and x3 minus x2. So this might be for the I equals 3 for a second order polynomial, just like we had this last one, I equals 3, and you'll see that's the equivalent term to what I just wrote by looking at the product notation here. Couple notes: each of the n weighting coefficients is going to be a polynomial of the same order as f. So if f is a cubic polynomial, then each L sub I, so if that's a cubic, then the L sub i's are each a cubic. And then the key thing, the thing that's really cool here, is that the weighting coefficients are calculated directly. We have not solved a linear system to determine the weighting coefficients. We've directly calculated these coefficients. There's no unknown that we have to solve with a linear system. We have no worries about round-off error or a Vandermonde matrix. We just follow this pattern, follow the formula here for the weighting coefficients, and formulate that polynomial directly. So let's look at how we can use Lagrange polynomials for interpolation. So here's some data, and we're going to find the value of y when x equals 2.3 using first and second order Lagrange polynomials. So first we have to see where are we interpolating in this data, and we'll find x equals 2.3 falls right here in between 1.5 and 2.5. So for our first order Lagrange, we'll make sure that our points x1 and x2 bracket the point where we're interpolating. So we will call this x1 and that x2 as 2.5. And then what we'll do is just plug these in to our first order Lagrange interpolating polynomial that I've rewritten here. So we have x1 is 1.5, so there's a 1.5 there, 1.5 there. We have x2 is 2.5, so that's going to be 2.5, 2.5, 2.5. And then the y data corresponding to that, f of x1 is going to be 3.2, and f of x2 is going to be 3.9. And then the value of x at which we're interpolating, that's that 2.3. So we'll plug that in here, 2.3 and 2.3. And now everything on the right-hand side of this equation is just numbers. So we'll plug that all in, either on MATLAB or just in a calculator, and we get f1, our first order Lagrange interpolating polynomial, for x equals 2.3 is equal to 3.76. Now, doing the same thing for a second order Lagrange polynomial, now we have 3 points. So the first thing we need to do is choose our 3 points. So let's look carefully. We have two choices. We can choose 1.5, 2.5, and 3.1, or we can choose 1.0, 1.5, and 2.5. And what we want to do is choose the closest 3 points. So again, we're interpolating at x equals 2.3. So 2.3 minus 1.0 is 1.3. 3.1 minus 2.3 is 0.8. So 3.1 is going to be closer to 2.3 than 1.0. So we'll use 3.1 as our third point and call that x3 for our interpolating polynomial. Then we're just going to go through and do the same thing we did with the first order Lagrange polynomial, and I would encourage you to try this out. Plug in all these numbers for x1, x2, and x3. For x, you're going to use 2.3, and it should be f2 of x. And you should get f2 evaluated at x equals 2.3 is 3.5967. So again, I'd encourage you to try that on your own. Plug that in with a calculator or with MATLAB and make sure you can reproduce that result. So there's some other applications of Lagrange polynomials. We can use them for interpolation, but because they offer a direct method to determine a polynomial passing through n data points, we can also use them in the development of several numerical methods, including the Newton-Cotes integration formulas. We're going to be looking at those next week. Differentiating data with unequal spacing. We'll also look at that next week. And Adams methods for solving differential equations, and we'll get to that later in the quarter. The bottom line is, since we don't have to solve a linear system, for interpolation, we don't have the round-off error problems, and also for developing other numerical methods, we can use Lagrange polynomials to develop a direct expression of a polynomial passing through some number of data points as we determine useful for that numerical method. And we'll see those examples in the weeks going forward.